The brackets, that confused Thomas for a minute there, because he thought that was my new handle, Zach Franken. Zach is my business partner. He's in brackets because he's not here, obviously. Yeah, we work for a company called Aperture Labs, and our day job is hardware reverse engineering. So we basically are breaking into stuff. We totally stole our name from a game. Any of you guys played Portal? Yeah, only one. Come on. Seriously? Okay. So we're not that other Aperture Labs, but we do get fan mail from time to time. Don't know how well you can read that. But this is some little kid called Joshua who's asking if we make portal guns. Which obviously we do, but we don't sell them. So Zach is the hardware guy. He's heavily involved in the kind of scary, analog-y, electronic-y world of pure evil. He does play a lot with scary chemicals, so when we're reverse engineering stuff, he likes to drill into chips with fuming nitric acid and stuff like that. So he's in charge of bad smells and scary chemicals. And if you know him, you'll agree that's quite a good representation of what he looks like. He doesn't have a dog, that's my dog. And then there's me. I'm on the nice digital side. My job is to convert all those horrible analog-y things into nice bits and bytes. So that's my goal, always. Get away from the evil analog world and into digital as soon as possible. Actually, that seems to be a recurring theme here. There's a lot of guys like me, kind of software guys, that are doing hardware-y projects and not really understanding how or why we get it to work. So I rely on my partner for that, and he just delivers me the electronics, and I do the digital stuff. As Thomas mentioned, I also run the London DEF CON group, DC4420. If you're ever in town, last Tuesday of the month, we normally meet. We have an open meeting. Anyone's welcome to come. Speakers particularly, submit your talks. We have 2 talks every month, and it's completely free, and it's in a pub. So like here, the alternate theme is drinking a lot. Okay, so what am I going to talk about today? Rfidler is the project, and it's a software-defined RFID, basically inspired by software-defined radio. So I'm going to talk about the kind of thinking behind it and how we decided to try and apply software-defined radio thinking to the world of RFID. I've been playing with RFID for a long time, but it's always been slightly dissatisfying. I'm having to use other people's tools, other people's hardware, and I'm hitting limitations what we can do with it. So this was like to try and break out of that jail. And why are we doing it? Well, even though I've been talking about this stuff for more years than I care to remember, manufacturers are still pushing this crap out. There's still physical security systems that are completely insecure. The tools for demonstrating the insecurities or researching the insecurities are pretty expensive. The best one out there is probably the Proxmark 3. It's a very, very good tool, but it's fragile. It's easy to brick it, basically, and it's pretty expensive. It's about $400 by the time you've put one together and put antennas and so on with it. The alternative is to look at, so we're specifically talking here about sort of access control cards for going into buildings and so on. And the alternative is to look at the development kits that come from the manufacturers themselves. And again, they're expensive, and they're generally locked into a single type, so you can't do much with them except research one particular tag type. And what we want to do is change that. Disrupt the market, change the landscape, make it easy for people to just pick this stuff up, start playing with it, and prove that the systems that are out there are actually not fit for purpose anymore, and they need to change. So when I started looking into it, I found it really confusing, and people still, when I talk to people about RFID, people do find it very confusing. Lots of different standards out there. A lot of it's proprietary, so they don't publish details how it all works. You think you're buying one brand, it's actually another brand with a slight tweak and a change to the name or whatever. And one of the first kind of starting points of all the misconception is that it's not even RFID. RFID stands for radio frequency identification, but there is no radio involved. What you actually have is inductively coupled coils talking to each other, and there's no radio. I mean, there is radio in some systems, but in most of what we're talking about, there is no radio involved. The data part of it, when you start looking at what data is actually being transferred between the reader and the tag, it only becomes digital like right at the end of the path. So every reader tends to have a circuit that's specifically designed to read that particular tag type, and then at the end you get a digital stream. So it's difficult to use, or impossible to use, one reader to read somebody else's tags. So again, you know, how can we change all of that? So we went to the idea of software-defined radio. So in software-defined radio, basically, the actual over-the-air transmission and reception is done in hardware, but everything beyond that first step is done in software. So all the modulation, the demodulation, filtering, whatever you want to do, mixing channels, whatever, goes in software. So your circuit is pretty simple, and you have a nice, powerful processor that then processes the signal and does everything else for you. So I use a thing called a fun cube. It was designed to go with a satellite project. So there are these cube satellites that get launched into space. Pretty cheap, I think it's about 30 grand to put a cube together. And then a whole bunch of them get launched together. So universities and things do these projects. And this was a project where they put a satellite up into space, and it's for students to experiment with receiving signals and processing signals. So it covers everything from 150 kilohertz to about 2 gigahertz. Really powerful tool. I use it a lot for other stuff as well. Very cheap. I think they're about £75. And it works with GNU radio. So if you're going to play with software-defined radio and you don't want to actually understand software-defined radio like me, I don't care. I just want the digital. GNU radio is a great tool because it just gives you building blocks. So you can say, okay, I've got a fun cube as my source. I'm going to take its output, do a bit of conversion to change the number to a suitable format to go to my sound card and to a WAV file. So I can now tune it to whatever frequency, receive some sound, stick it in a WAV file, and I'm on my way to getting actual digital data. So here's an example. I've just tuned it to whatever frequency, captured some audio, and we can see straight away that this isn't audio. You know, it's too structured. It's not, you know, the latest pop song. Actually, it could be Miley Cyrus, couldn't it? So yeah, it's clearly not musical. If we zoom in, we see this. So basically, you've got some pulses and some silence. Little pulse, silence, little pulse, silence. This is amplitude modulation. So we're increasing and decreasing the amplitude of the signal. In this case, it's going from all to nothing. So that's what's known as on-off keying. So we're just sending little bursts of traffic, and that's AM/OOK, on-off keying. So now I know it's AM. You know, it's obviously recognizable as AM. That much I do know about analog stuff. I can change my numeric conversion to an actual demodulator. So GNU radio has a building block that will take an AM signal, convert it to something more sensible. So it's going to demodulate the AM for me. So if I run it through that and now look at the signal again, I start to get something that looks more like a data trace. Okay, so it's still a bit wobbly. But at this point, it's in a WAV file. So a WAV file is just a header and a bunch of numbers. So I can write a bit of Python that takes that WAV file and processes the numbers. So in this case, I just say, okay, everything that's below 0 becomes minus 32,000. Everything that's above 0 becomes plus 32,000 or whatever. And I convert it into a nice clean square wave. So now, with very little effort, we've got actual raw data we've pulled out using software-defined radio, and we've now got something that we can turn into a bit stream. So if we look at that and we want to convert it to a bit stream, just take the shortest pulse, say, okay, that's our pulse width. If it's high, it's a 1. If it's low, it's a 0. Simple as that. That's double width, so it's 2 1s. So bingo, we're now into binary, and I'm happy. So that's how software-defined radio works. So can we apply that to RFID? Why not? So similar thing, the reader is generating 125 kilohertz carrier wave. The tag, when it's placed in the reader field, the coil gets energized because they're inductively coupled. Tag wakes up, takes its power from the coil. The tag communicates back to the reader by grounding its coil. So because the coils are inductively coupled, anything the tag does to its coil will affect the reader coil. So if it shorts its coil out, there's going to be a voltage drop in the reader coil. The reader can detect that. So here we are, tag is signaling, and we can see the effect that the tag is having on the carrier that the reader's generating. On the other side, if the reader wants to talk to the tag, he can just simply stop sending a carrier, and the tag notices this gap and says, okay, I'm seeing a message, and what the tag does is it measures the width of these pulses, and that pulse is a 1 or a 0. So again, we're back to ASK and OOK. So the reader, when it energizes its coil, is on, and when it's not, it's off. And when the tag's grounding its coil, it's on, or it's not, it's off. So exactly the same principle, on-off key. So one of the things I found really confusing when I started all this is, okay, I can understand ASK. That's pretty simple. And that's all there seems to be. If you look at the low level, there's nothing else you could really do. You can ground your coil or not ground your coil. You can energize the field or not energize the field. That's it. So how do we end up with all these other things? PWM, FSK, PSK, Manchester, and so on. So, like I said, I found that really, really puzzling. So if we look at each of those modulation schemes, we've already done ASK. That's easy. So ones and noughts, we either ground our coil or don't ground our coil. And if you run that through a demodulator and take away the carrier, you end up with a signal that looks like that. So highs and lows, same as my wave file square wave. And again, we can just split it up into ones and noughts. Nice and easy. Manchester encoding is just the same thing, only you're adding another layer. So for each bit, instead of keeping your modulator running the same as the data, you actually modulate halfway through the pulse. So a 1 becomes a 0 or a low high, and a 0 becomes a high low, or vice versa. Now this is quite magic because it actually adds a layer to the data so you can use it, because the only valid bit stream within Manchester is either a 1-0 for a 1 or a 0-1 for a 0. If you see a 1-1, that's invalid, and if you see a 0-0, that's invalid. And that helps you because, for example, in this bit stream, we started with a 1-1. So that's invalid, so what do? Basically, we just skip half a bit. So we literally throw away that first one. So if we divide the data up into pairs, we get 1, 1, 0, 1. The 1, 1 is invalid. So throw away the first one, skip half a bit, and you've now got only valid pairs. So that means we've synchronized ourselves to the transmitter's clock. So we now know where the beginning of our bit period is. So that's achieved quite a useful function for us. It also allows us to detect errors. So the first error wasn't an error, it's just because we started reading half a bit off. But if we see another 1, 1 or another 0, 0, then we know we've seen an error. So we've actually got a bit stream error. You also get the ability to actually transmit a 0. If you remember the original ASK, a 0 was just an absence of signal. So what's the difference between me not transmitting and me transmitting 1,000 zeros? There isn't one. But with Manchester, you can actually transmit a 0 because a 0 is actually a 0, 1. So again, a useful facility. Okay, biphase, very similar. The only difference is you only modulate in that way for a 1. If it's a 0, you just flip the bit. But you keep it the same throughout the bit period. So here's where it gets clever. So FSK, frequency shift keying. What you actually do is you modulate the signal in the same way, but you just do it much more frequently, and you do it at a different rate depending if you're sending a 1 or a 0. So we're going to ground our coil multiple times during the bit period, and for a 1 we do it very quickly, and for a 0 we do it slightly slower. And that has the effect, if you run it through our demodulator, of creating a pattern like this. So the carrier's breaking through for a short period, and then it's being squashed, and then it's coming through again, and so on. And you can see you have thin spikes, and you have thick spikes. So that's FSK. So we've magically generated FSK using ASK on top of an existing carrier, which was a revelation to me. It's like, oh, that's how it works. That was easy. So this is a diagram showing, this is when I'm damping, so the red is when I'm damped, and the black gaps is when I'm not damped. And you can see the carrier just coming through in little bursts. And to convert that back to data, we just count the spikes. So within our bit period, if we get 6 short pulses, it's a 0, and if we get 5 long ones, it's a 1. Very simple. PSK, phase shift keying. So phase shift keying is where you're modulating away, and when you want to signal an event, you change your phase. So in this case, you just pause for an extra period. So if you're currently damped, you just damp for another period. And if you're undamped, you undamp for another period. And that has this effect. When I first saw this, it was like, woo, what the hell is that? And basically what's happening is, because you're damping at like 50% of the rate of the original carrier, this carrier is trying to burst through. So if we were not damped at all and there was no tag in the field, the lines would go all the way from the top to the bottom, and it would just be a big solid bar. What's happening is, during this period, we're damping it for half the time. So the carrier gets about halfway up, and then it gets squashed, and then it heads down, and it gets squashed. Whenever we modulate, it bursts through for just one period, so you get these spikes, either high or low. So the pink bit is where we're damping for 50% of the time. The red bit's where we're fully damped, and the black bit's where we're undamped. So you can see you get a spike coming through where it's undamped, or a drop to the bottom when it's fully damped. So again, it kind of makes sense when you understand what's going on. And to convert that to data, you simply measure your bit period, and whenever there's a spike, you flip the bit. So if there's no change, if this was a 1, that's just 1, 1, 1, 1, 1, 1, we hit a bit, becomes a 0. 0, 0, 1, 1, 1, 1, 0, 0, so on. So again, really easy to convert back to digital. And as I mentioned earlier, on the other way round, when the reader wants to talk to the tag, it just does pulse widths. So a fat pulse is a 1, thin pulse is a 0, and what it's doing is just switching off its carrier. So the tag has a little capacitor in it that allows it to store some energy, so even though the carrier is turned off, the tag doesn't die. It has enough energy to survive that little gap and carry on to the next pulse. Okay, so that's the low-level basics. Now we're going to look at the actual data, what's being sent across between the reader and the tag. So generally, most tags are passive. You stick it in, or at least at this frequency, the 125 kilohertz stuff that we're looking at. You stick the reader into the field, it spits out an ID. It just starts barfing out numbers. Even if it's encrypted, so there's a standard called Indala, and basically they just take the content that they would normally send and they encrypt it, and then they send that, but it's still the same thing. So a replay of that data will work just as well as a replay of an unencrypted stream. So it literally is about as secure as a barcode. You might as well just print a number on a piece of paper and hold it up to the reader, and the reader recognizes the number, it lets you in. Active tags, on the other hand, there's a two-way communication. So spits out an ID, and then the reader will, based on that ID, issue a challenge. They might do a two-way authentication. And that's more secure, but it's only as secure as the underlying crypto. So HiTag2, for example, has been broken for a couple of years. DesFire, as far as I'm aware, is not broken. There are some particular attacks. I mean, we've actually recovered keys from systems that were badly implemented, but the DesFire tags themselves are fine. So the thing we've designed is called Rfidler. This is the low-frequency version. The plan was to make it very cheap, make it very easy to use, quite powerful, useful as a standalone device, so you can just plug it in and use it. You don't need a whole lot of processor or anything. And what it does is it provides you with the analog circuit that does the initial ASK, and then everything else is done in software. We did a Kickstarter project to fund it. It's actually, this was the original price point that we wanted, so we were aiming for 30 quid. Like all these projects, we've just gone mad and added more and more features to it as we've gone along, so that's actually probably going to go up. But it's also going to be entirely open source. So the software is open source. The circuit design is Creative Commons. So you'll be able to just download it, build it yourself. You don't have to give us anything, or you can pay us what it's going to cost us to build them, which will probably be about $100 in the end. Kickstarter's closed, by the way, so we're about to go into hopefully into our first production run, so there will be some left over from that. So we will be sticking them on the website for sale. So this is the plan. It should be able to use any modulation scheme, should do bidirectional protocols, should be able to read a tag, write a tag, emulate a tag, sniff conversations between tag and reader. As I said, be totally standalone, easy to use. Tag types it already knows about and can deal with. EM4102 is a very common tag type. Actually, these guys, it's one of the first ones I ever cloned. I publish an RFID library called Rfidler. And I have tools in there for cloning these onto a Q5, which is a very flexible tag type that you can reprogram to emulate other tags. These are very, very common, and strangely, they're the most common in alarm systems. So if you're in the UK and you have a monitored alarm system, the police will only respond to your alarm system if you use an RFID tag to enter the building and switch the alarm off. If you use a PIN, you cannot sign up to have police monitoring. So they mandate it has to be disarmed with an RFID tag. And the RFID tag type that's most commonly used is an EM4102, which is trivially clonable and generally comes in the shape of a key fob, which will be on your key ring. So when you lose your keys, you lose your fob, and someone can just pick them up and walk into your building and turn your alarm off. So it's a great idea. Well done, the police. Okay, so how software defined is Rfidler? Basically, as I said, the hardware does just the ASK demodulation for you. Everything else after that is done by the chip, including generating the carrier, demodulating FSK, PSK, Manchester, PWM, whatever. So the only bit that the circuit does is ASK. So here we have an example. Fiddler's getting, this is the signal generated by the ASK circuit, and this is actually a PSK signal coming in. So the up and down pulses are both converted to ups. So all we have to do is detect the up. And where there's an up, we've got a spike, and then we process that into a bit stream. We can also emulate. So one of the things I found quite frustrating, I mean, I'm a great fan of the Proxmark. Has anyone here actually used a Proxmark or have a Proxmark? A few of you, okay. So one of the things I find frustrating with the Proxmark is the way the software is designed is that it's very sort of top-down. So when you're looking at a particular tag type, all the code for dealing with that tag has been written purely with that tag in mind. So, you know, the code for reading a HID tag or the code for reading an Indala tag is entirely self-contained for reading a HID tag, and it does everything. It like takes some data from the coil and it processes it, and it gives you the output for HID or Indala or whatever. Our approach has been to actually start at the low level, so deal with the modulation scheme first and then layer the tag types on top of that. And what that gives you is a lot of flexibility. So you can basically say, okay, there are only 4 different modulation schemes. There's pure ASK, there's PSK, there's FSK, and then there's Manchester and so on layered on top of that. So if we implement those properly, then we can pretty much do anything. So now if you want to emulate a bit stream, you can just say, well, I want to do ASK and my pulse width is this, or my data rate is this, and here's the bit stream, and off you go. So it's very trivial to implement those kind of commands because the low level's done for you. Similarly, Manchester, you can just flip a bit to say, well, it's Manchester, and the ones and zeros get converted appropriately to high lows and low highs. Again, FSK, you tell it what the 2 data rates are, tell it to spit out some binary, and it does that for you. Similarly, PSK. So this was our first attempt. As you can see, it's a bunch of spaghetti because it's basically software guys trying to do hardware. So we use this thing. This board is called a Bitwhacker. It's a Bitwhacker 32. It's a very powerful tool if you want to play with hardware and you're not really a hardware guy. This is a very powerful PIC32 processor, and it has a whole bunch of buses already built into it, so you can do stuff like smart cards, you can do CAN bus, pretty much anything, I2C, whatever. So we use it as a standard platform for development. We've got a whole library. We have our own little toolkit called GIFT, which is general purpose hardware hacking tool. and we basically develop routines in here for driving stuff. So our first attempt took one of these, and it talks to this little analog circuit here. This is connected via all this spaghetti to a reader, sorry, that's an emulator coil and a reader coil. And this is a logic analyzer, so I could see what the hell was actually going on. This is version 2. We've now put that circuit into a circuit instead of a bunch of spaghetti. Still got the same bitwhacker 32 as the main processor. And now you've got a couple of headers so you can switch between reader and emulator. And then Chipmonkey steps in and does some kind of weird voodoo magic and generates something like that. So this is the final circuit. So, yeah, I said we've been playing a lot, so this is version 20. And actually, the one I've got here is version 22, because on my way to Vancouver, a guy met me at the airport. I literally had a cab driver arrive at the airport at the same time as me, and he handed me version 21. And the day before I flew out here, I had to go to Zach's house and pick up version 22. So I'm hoping this is the last one. But every time I get back, he's added some more features. So we've now got smart card and SD card and all sorts of stuff on there. So this is where I'm hoping the gods are with me, and I'm actually going to do a demo. So I'm going to show you how this thing works. So basically, when you plug it in, it just goes into the USB. It presents itself as a CDC serial port. So here we have product ID, Rfidler LF, and it's come up as a TTY. So I can just use any serial emulator to talk to it. So if I use Minicom, and actually, if you don't want to use USB, it will detect a TTL connection as well. So you can connect a standard serial port to it as well. Okay. So as you can see, it's got quite an extensive menu. You can do a whole bunch of stuff. So what we've tried to do is create pretty much all the commands you would want to do. If you want to test a system or analyze a tag or copy a tag or whatever, we've got built-in commands to do it. It's very easy to extend, as I said, because we built this framework. You can configure it to say what type of tag you want to play with. It sets a bunch of parameters, and those are very easy to generate new ones. When you come across a new tag type, you just figure out what the parameters are, set them up, and you've added a new tag type. So if I say tags, it'll tell me the current tag types that it knows about. We're currently set to unique, which is a standard. And if I do a config, these are the parameters that you have to set. So you tell it if it's ASK or FSK, whatever, if it's Manchester, biphase, if the data's inverted, the data rate, and so on. So it has a concept of two tags. You've got the real physical tag, so whatever this prompt here is, that's what you're currently set to. So currently we're set to unique, so if I find a unique tag, stick it on the coil, and do a UID, of course I get a read error. Actually, I'm thinking it's this metal table. That's probably not helping. Yeah, this is going to be fun. Does someone want to come and help me by holding these tags off the metal table? All right. Yeah, no, it's not going to work. Hang on. Thanks. Okay, so yeah, metal and RFID just really don't go together. So as you can see, we've successfully read the UID. Can you read this at the back? No. Is that better? Yeah? Okay. So we've read the UID. So in this case, it's this number. What I can also do is say, copy that. So if I just say copy, it says, okay, I've copied. You'll notice that we also get a little asterisk here. That's to say that something's changed. So the config has changed, but we haven't stored it. What's actually happened is we've now created a virtual tag. So vtag now has a copy of that tag in its memory. So this is the UID as unique would define it, and this is the raw bit stream that actually goes over the air. So we remember that. And it's been copied to a Q5 by default. So the Q5 is the tag that's configurable to be any kind of tag you want it to be. So what I can do now, now it's in memory, I can also emulate. So this is a standard reader. If Thomas holds the tag up to this reader, it'll go beep, and it's given me an ID. If I now do the same thing and just hold the reader up to the coil, of course nothing happens. The curse of the demo. Bastard. This works every time. There we go. So it's now read from the emulator. The other thing you can do is tell it to actually write to a Q5. So this is a blank Q5. If Thomas holds that to the tag, I can just say copy. Try another one. This really is unbelievable. Just hold it flat like that. Okay. Oh, sorry, I'm being an idiot. Copy is reading, clone is writing. Don't even know my own kit. So copy copies from the physical tag to the virtual tag. Clone writes from the virtual tag to the physical tag. So as you saw, what I actually did now was I encoded an arbitrary value from unique to Q5. And if we look at the V tag, we're running unique. And if I read that, so again, that just reads from the Q5, which is now emulating that tag type. The other thing you can do if you're examining an unknown tag is on the back end of all these readers, there's an industry standard called Wigand. So Wigand is the wiring that's used from a reader to talk to the back-end system. So this is a standard HID reader. HID is like the one of the biggest manufacturers in the world of this kind of stuff. So if we plug a native HID reader into Rfidler, we can actually do a Wigand read. Okay, we're finished with that. Thanks. You're done. Thank you. Yeah, thanks. Thank you, Thomas. So if I go Wigand read, so it's waiting for the external reader to talk, and if I present a native tag, it's now read the data. It's measured the pulse width. So in microseconds, it's 39 microseconds with a gap of about 2,000 and a bit period overall of just over 2,000. So if we wanted to, we can now play data back on the Wigand bus using the correct timings, because we now know the timings for this reader. If I take this bit stream, the first 8 bits is what's called the site code. So we got a site code of 6, and a UID of 30115, which is actually what's printed on the back of this card. So we know now that the data being sent over the back end matches what's on the card. And with any luck, if I say, where the cursor of the demo kicks in again. So there, we've successfully read, using the coil, we've read the same data. So we got a site code of 006 and a UID of 30115. So that should match that raw data. So we know we're definitely reading the right data. So if you're analyzing an unknown tag, that's an enormous step. You know, on a HID, before you had no way of knowing what the site code was and what the UID was. Now you can actually do it in a few simple steps. You can figure out what the hell's going on. It's also extensible. So there we go. If you don't want to use the menu system, you can just use a Python wrapper. So we've written a Python wrapper for it. Okay, it has crashed. It's the last time I ever do a live demo. Yeah, so a normal ping will just reply Rfidler, and then you can do stuff like set tag HID26, emulate. And if I put the coil on the native reader, so we just emulated a tag. And I think on that happy note, I'm going to call it quits.
You want to buy?
Can you buy one now? You can put your name down for one. They'll be out in hopefully about 2 weeks, 2 to 3 weeks. One thing I was going to quickly say was at the conference I was at in Vancouver, one of the guys was staying at a nearby hotel where they were using an access control system I'd never seen before. And because of the modularity of the system, it was really easy to take an existing, we had a look at the reader and we found the name of the device was called AWID. We found someone had already done an analysis of the low-level stuff, which was here. So we downloaded his data sheet and he talked about, what frequency it is, it's FSK, this is the data rate, this is the bits and so on. And literally within an hour, we had added that format to Rfidler. So now you can just set the tag type to AWID26, encode any number you want to a Q5, it generates the appropriate data, hit clone, it writes it to the tag, and that tag just worked first time. So that framework really works. It's really easy to just add new stuff to it. So literally 1 hour from seeing the first tag to going and walking into the building.
My question mainly is that, let's say you wanted to test an RFID system, and you have like 1,000 keys that you want to test, 1,000 RFID keys that you want to test. How do you automate that process? Or is this does your framework allow you to do some kind of automation, or do you need like to move the coil back and forth or trigger something?
Okay, well, yeah, as it happens, the current thing that's holding up production is I'm working on a test rig, and so built into the framework is a test command. So if I run Rfidler with no it'll just give me a help. So sorry, let's try help. So if we look at the menu option, there's you've got a bunch of debug pins. So the debug pins, you can switch them on and off. So you could wire something up. I mean, I don't know how you're going to feed 1,000 tags, but if you've got some kind of activated feeder, then you could have Rfidler pinging the tags. Oh, if the card's changing all the time. Yeah, well, with the wrapper, with the Python wrapper, you can do whatever you want. So, you could just say UID, so while 42, do blah, whatever, just write a loop. So you can write whatever code you want to wrap the commands and do whatever you want. So in API mode, it just gives you back the raw data, what it got back from the command you sent. Is that what you mean? Oh, I see. You want to brute force an ID onto a reader. Yeah, sure. So, well, the emulate command that I sent an emulate command here, which was emulating site code 1, 2, 3, 4, 5, 6, 7, 8. I could easily put that in a loop, which then did 9, then 10, then 11, whatever. And you could hook up a sensor maybe to the light, so when it gets a green light, then it knows that the door opened. So it'll automatically stop when the door opens.
Hey, you mentioned doing the modulation, demodulation in software. So I was curious on the performance. Was it more or less performant than using a dedicated hardware modulator, demodulator?
Okay, so basically what we ended up doing is the ASK modulation circuit just gives you a data point whenever there is some modulation. So if it's PSK, you get a spike. If it's ASK, you get either a high or a low when the carrier's there or not there. If you were trying to actually demodulate the 125 kilohertz at that level, you would be having to process 125,000 events per second. And that's why things like the Proxmark use an FPGA, because we're not trying to do that, because we've done the very low-level modulation in an analog circuit. We're only dealing with a few thousand events per second. So a PIC is easily powerful enough to do it. And in fact, the way the project's designed is you can discard the PIC side of the circuit and just take the analog side. And if you want to drive it from an Arduino or a BeagleBone or whatever you want, then you can, and you just write your own firmware for it.